We're going to get started again. Next speaker is Giulio Chiribella, talking about optimal compression of identically prepared states.
Thank you, Mark. And first of all, I would like to thank the organizers for the tremendous work of putting all this together. So today I'm talking about a special type of quantum compression where we want to prepare to compress states that have been all prepared, equally prepared. So this is a joint work, mostly with three people. Shannon is the person who has kind of been common in all the works that I'm presenting today. Ishan and Daniel are students of mine in Hong Kong. They are both here attending QIP. So the other author is Masahito Hayashi from Nagoya University and CQT Singapore. So I will present two works which are related, and I will contrast and compare them. So the first is with Ishan and Daniel. And the second is with Ishan and Masahito. So these are both papers about this problem of compressing identically prepared states, but under different conditions. So let me start by introducing the task. The task is the following. So imagine that you have a machine that prepares quantum states. So this machine is promised to prepare every time the same quantum state rho x. So it's a preparation device. Every time you press the button, the machine will spit out the same quantum state rho x. The thing is that you don't know what x is. So ideally, you would like to compress, to store this information that is produced by the machine in the smallest amount of space, of memory space, without knowing what is x. So you only have a prior knowledge that x should be in some set of states, into some parametric family of states, labeled by some parameter x. So the question that I will consider is like, how much memory do we need to store n copies of the state rho x? There is another related task that somehow is studied also here, is the task of describing a state preparation. So in this case, think again of the source that produces n copies of the state rho. So if this source produces the state rho, inside there should be a description. There should be a set of instructions that tells the source which state it should prepare. So a state preparation device that manages to prepare almost the same state all the time should contain some information about the state inside. So one question is like, what is the shortest description that nature could store into the preparation device in order to make it able to produce copies of the state? In a more cartoonish version, we can imagine a similar situation where there are two parties, Alice and Bob. So Alice wants Bob to prepare a state for her, and she wants to communicate communicate to him which state she wants. So she would prepare a message, generally a quantum message, to tell Bob which state he should produce. So Bob would have a programmable state preparation machine that will produce approximate copies of the state that Alice wanted. And again, the question is, what is the shortest message that Alice should send in order to describe the preparation for Bob? So it turns out that asymptotically, when n is large, the two tasks are equivalent. So the amount of information, of memory it takes to store the data produced by the source is the same as the minimum, the size of the minimum message one has to communicate in order to instruct a party to prepare the same state. So in the following, I will focus on compression. So I will always talk about the compression of identically prepared states. But keep in mind that this also applied to the question of what is the minimal description of a source. So why do we care about this? Well, for many reasons. One is like that many problems in quantum information processing, like optimal cloning or optimal purification, even state discrimination, and most recently machine learning. So many of these problems use as an input data many copies of the same quantum state. And the goal of the game is to use these copies coherently, not just to measure them, but to do some coherent operation on the input copies. So one recent example is this quantum principal component analysis by Lloyd et al., where you start from many copies of a quantum state and you try coherently to produce a unitary gate that depends on that state. So of course, if you wanted to do it with quantum operations, you have to have a quantum machine that does it. And typically, a quantum machine will have a limited amount of memory where the input copies can be stored. So it is important to find a way to compress and to store the data in the most efficient way. So this doesn't apply only to quantum tasks like cloning or machine learning, but also to more classical tasks where you want to distinguish the states. Even in that case, so there is this very nice paper by Sarah, Robin, and Michael on distinguishing states where you collect the information over time by storing them in a memory. And again, the problem of storing the state in the smallest amount of memory is relevant even when you plan to measure the state. So another obvious motivation is quantum communication. You may want to transmit the information about many copies of the same state using the shortest message. This is going probably to be important in the future when we'll have quantum sensor networks where you want to transfer information collected from many nodes and send it to a central station where the information is processed. There are also some very interesting related topics. One is an area of classical information theory on the minimum description length. That is a very classic topic started by Shannon. So essentially in the work done in this area, the compression of identically prepared probability distributions is an intermediate step to establish the minimum description length. Another related area is the area of quantum Kolmogorov complexity, where the question is like to find what is the shortest quantum circuit that generates a given state. So the flavor of quantum Kolmogorov complexity is more complexity theoretic, while in this talk I will focus on information theoretic questions. So I will not care about the gate complexity. I will not care too much, at least, about that, but more about just the size of the memory. Okay, so much about the motivation. A little bit of a caveat. So we shouldn't confuse this type of compression that I'm talking about with the usual Schumacher compression. So in Schumacher's case, there is a source that produces states in a way that is IID. So every time you press the button, the source will produce a random state that depends on a different x every time. So this source will give you a sequence of different states with some probability distribution that is always the same for every use of the source. In our case, the source produces always the same state. So there is a perfect correlation between subsequent uses of the source. So what we have is rho x tensor n instead of rho x1, rho x2, rho xn. And notice that I didn't put a probability distribution here because literally we don't need it here. It's pretty irrelevant what probability distribution I will put here. So it's a really different setting. So you cannot use the results from Schumacher compression to understand this particular problem. The rates are very different. Everything is totally different here. Okay, so let me formulate the problem a little bit more mathematically. So as always in compression, you have our input data, the n copies. They go through an encoding channel E. So what we will get is a quantum state of a memory. And then the memory will go through a decoding channel that will try to reproduce the same state that we had at the beginning, the identical copies. So our states belong to some parametric family, rho of x. Our input is n copies of rho of x. As an error, I will consider the worst case error over all possible states that we may want to compress. So again, no probability here, just worst case over all possible values of x. And at least for the moment, I will care about the total memory size, so the size of this memory. For the moment, I will not care about how much of this memory can be made classical and how much of it is quantum. I will just care, at least for most of the talk, about the total size of the memory. So we'll take the dimension of this memory system, take the log, so I will measure it in qubits, and see how small we can make this. So the problem is for fixed n, for fixed number of copies, and for fixed error, for fixed epsilon, to find what is the smallest amount of memory that we need to encode the input copies. OK, so let's, as a warm-up, start first from the case of pure qubits. So in the case of qubits, this problem was studied by PLESCH and BUZEK in 2010. So it's quite natural to see that if you have n copies of a pure qubit state, you can compress it without any error into log n plus 1 qubits. So you can compress it in an exponentially smaller space, which is nice, and it's very intuitive why you can do that. Because if you write the qubit state as a linear combination of 0 and 1, you tensor it for n times, so you expand everything. So you will have one vector where you have all zeros, one vector where you have 1, 1, one where you have 2 ones, and so on. So the number of basis vectors that you get here is n plus 1. So this state lives in an n plus 1 dimensional subspace, the symmetric space. So the number of qubits you need is log of the dimension, so it's log of n plus 1. So that's an easy observation. So the interesting thing here is that you can do this in an efficient way. So the way to encode the data is to use what is called the Schur transform. The Schur transform can be realized approximately with a polynomial number of gates. This was shown by Bacon, Harrow, and Chuang in 2006. Well, here we care more perhaps about exact realizations, because this was for a perfect compression. So BUZEK and PLESCH showed that if you want to compress pure states, you can implement the Schur transform exactly with n square number of gates. So this was probably the most interesting result in the paper by BUZEK and PLESCH. And using this particular realization of the Schur transform, there's been an experiment implementing this exact compression from 2 to 3 qubits by the group of Ephraim Steinberg in Toronto. So here there is a scheme of the experiment. Here there is actually the fidelities that are quite good. Of course, there are always experimental errors, but so yes, it was very nice because we could see a real experiment of information compression. Of course, in experiment there is an error, so it's also interesting to ask what happens when we allow for a non-zero error. And so this is one of the first questions that we started to address in the paper with Yishan and Daniel. So the first thing is to consider like non-zero error and higher dimensions. So it's still easy. This part is still easy. It's easy to show that you can compress n copies of a pure state in the symmetric subspace. So now you need d minus 1 log n qubits at the leading order. And if you allow for an error, well, this doesn't really change. Sorry, whatever. Yes, so this is the best we can do with no error. And even if we allow for an error, we cannot really do much better. So pretty much the rate remains the same, still d minus 1 minus epsilon log n. So the error really doesn't change much. For pure states, there is pretty much irrelevant whether you want zero error or a small non-zero error. So the next interesting question is what happens if we don't have pure states, but mixed states. So this, of course, is experimentally relevant, because in an experiment we really never have a pure state. So it's good to ask what happens for mixed states. And let's start from the exact compression. So here the key tool is the Schur-Weil decomposition of n copies of a mixed state. So what we can do is to decompose the state in this form. We have a mixture of orthogonal blocks labeled by some number j. So for dimension 2, this j is the angular momentum, is the spin of the system. For higher dimension, this is like the charge associated to the SU2 group. So we have a sum of blocks, and each block has this tensor product form. You have the information that is encoded in one part of the tensor product here, and we have on the other side, in the other part of the tensor product, we have a maximally mixed state, which we can think of as noise. So it's pretty much clear here how we can save space. The way to save space here is to throw away the noise, so to trace out this part, because anyways it doesn't contain any information about what state we have. So this idea was, I think, used for the first time by Kouachi and Emoto in 2001. It was essentially used in the paper on state discrimination that I mentioned before by these authors. So pretty much the idea is just to throw away the noise and to keep only the information that is in these blocks, in these representation spaces. You can see that just already this reduces the amount of memory by an exponential factor. So we did a little bit of exact calculation to see how much memory we need. So for mixed states of rank R in dimension D, we need this amount of memory. The exact number is not that important, but I mean, it's good that we can quantify it exactly at the leading order. So this protocol works pretty much for every state that has a rank R. If you have some generic state, so with maximum rank, with no degeneracy, and with arbitrary eigenvectors, we can show that even if you fix the spectrum of the state, this protocol is still optimal, as long as you want zero error. So pretty much this is the best we can do when we fix the error to be exactly equal to 0. So what happens if you allow for a non-zero error? So then we have an achievability result. We can show that every time we know the spectrum of our set of states, and we allow for a non-zero error, we can reduce the amount of memory by a discontinuous amount. So as soon as we allow for a small error, we can reduce the total memory requirement to this value, which is, well, the expression is similar to the one before, but the coefficient is smaller. And there is also a dependence on the degeneracy of the eigenvalues here. So this, well, it's nice that we have this further opportunity to reduce the memory. It's also nice that if we go to the next orders, the dependence on the error and on the total number of copies is very benign, is log-log. So it's, essentially the leading order is kind of much bigger than the next order. And of course, the question is this protocol optimal or not? So we didn't manage to prove optimality in full generality. We managed to prove optimality under assumptions. One assumption was that the encoding channel is covariant under changes of basis. So it's like if you rotate your input qubits, is the same as rotating your encoded state in some representation of the group. And the main assumption was that the decoding channel would preserve the charges, which means for qubits that the decoding channel preserves the angular momentum of the system. So we are not changing the value of the angular momentum here. And we will see later that this assumption is pretty crucial here. So the protocol is optimal only under assumptions here. So what are the ingredients of the proof? So the first ingredient is, again, the Schur-Weyl decomposition, where we throw away the noise. The next ingredient is a concentration of measure result that is pretty standard by now. It was used by Kyle and Werner and other authors later. Essentially, it tells us that the probability distribution on these blocks, on J, is concentrated around the typical value in a ball of radius square root of n. So we don't really need to encode all these subspaces, but only the relevant ones where all the probability is concentrated. So this is a pretty standard result. What was a bit of a headache for us was to actually find matching upper and lower bounds on the total amount of dimensions that we need. So there was a lot of combinatorics going here in order to be able to quantify what is the compression rate exactly after we throw away the low probability parts. Of course, the questions that are open, that were open in this work are, can we prove optimality without any assumption? And the other question was, what if we don't know the spectrum? How can we compress if we don't have a perfect knowledge of the spectrum in advance? So the next work was the one by, well, with Shannon and Masahito, was actually the full optimization in the case of qubits. For qubit mixed states, we have this full answer to the problem. So let me give you the theorem first for known spectrum and then for unknown spectrum. So for known spectrum, we showed that there exists a compression protocol that compresses all the mixed states with the given spectrum, with that particular spectrum, with an error that vanishes asymptotically for large n, and using a memory size of log n qubits at the leading order. So if you remember from before, the value that we had in our previous protocol for qubits would give 3/2 log n. So it was not actually the ultimate optimal protocol. It was only optimal under the assumptions that I mentioned. So this value, log n, now is unconditionally the optimal value for compression. So it's really, from information theoretic point of view, is the best we can do. So let me tell you a little bit about the proof of how do we get this rate. So the first step is that for qubits, the J, as I said before, is just the angular momentum, is the spin. So if we take an even number of input copies, this goes from 0 to n/2, the total angular momentum of the system. The second step is the one I already mentioned, is the concentration of measure. So the angular momentum will be in a strip of size square root of n around a value, J0, that is pretty much a constant times n. So we have these values that are the relevant ones. We can throw away all the rest. And now the key idea here, the key innovation that came with this new result, is that when you decompose a qubit state in this Schur-Weil decomposition, well, the states that you get in two blocks with the values of j that are close enough are equivalent to each other. So you can interconvert the states rho j with the two different values of j, j and j prime. You can interconvert them with an error that it is as most j minus j prime divided by n. So pretty much as the angular momentum is not too different, the states that you have in these blocks are giving you the same information, up to a small error. So you see where this is going. It's going here. So by Schur-Weil concentration, we can stay in an interval of square root of n, of size square root of n. So if the difference is at most square root of n, this error will go to 0 as 1 over square root of n, because get square root of n over n. So this tells you that all the typical states, rho j, are pretty much equivalent, information theoretically, to the rho j 0, to the single block that is in the center of the probability distribution. So this is, I think this is really the most interesting result that we had in this paper. And let me comment a little bit more. So in summary, what we have is that this whole tensor product of many copies, which is equal to a sum of many blocks, is actually equivalent to a single block of the sum, information theoretically. So up to an error of 1 over square root of n, plus, well, up to some constant. So up to this error, all this tensor product of states is just a single block with a fixed angular momentum. So we can now compare our two protocols. We can compare the protocol with well, the ultimate optimate compression with the one with where we assume the conservation of the spin. So in the optimal protocol, we get log n. In the one where we fix the conservation of the spin, you get a 3/2 log n. So you can see here this interesting physical idea that the compression, the amount of compression, depends on the assumption of the physical operations that we can do. So allowing to change the values of the angular momentum by an amount of square root of n allows us to save 1/2 log n qubits. So it's really a one-to-one correspondence between the physical resource of changing the angular momentum and the amount of qubits that we can save. So you see, this is the log of square root of n, essentially. So yes, the moral here is that if you just look at information theory, the optimal memory size is log n. If you look at the kind of conservation of the angular momentum, you cannot get to the optimal information theoretic value. The other nice comment that I should make here is that these conversion operations that go from rho j to rho j0 are essentially the optimal universal cloning and the partial trace. So yesterday we heard the talks about the duality between cloning and partial trace, this whole recovery maps businesses. So this is pretty much an instance, I would say, of these general ideas about recovery maps. So you can convert different values of the spin from one value to the other by using essentially quantum cloning and quantum partial trace. So it's nice that cloning becomes also a primitive for doing optimal information theoretic tasks. So it's like a new application of quantum cloning. Okay, I was saying there is also a result when you don't know the spectrum. So if the state of the qubit is completely unknown, is a completely unknown mixed state, you can still find the compression error that is optimal, has vanishing error, and uses now 3/2 log n qubits of memory. So the idea is pretty simple now that you understood the protocol with the fixed spectrum. So the idea is that if you don't know the spectrum, you just discretize the possible values of the angular momentum from 0 to n/2. You divide them in intervals of size square root of n. Then you measure the angular momentum, you measure J, and you pretend that you knew the spectrum, and the spectrum was the one corresponding to the states in that particular interval that you found. So you apply the previous protocol, pretending that you know, pretending that you know the spectrum. And this is pretty much the optimal thing you can do. So just discretize the spectrum, discretize the angular momentum into intervals of size square root of n, and then apply the protocol with known spectrum. We can prove that this is actually optimal in the ultimate information theoretic sense. So here is a little bit of a schematic of the protocol. So we start with the Schur transform to write everything in the nice decomposition. Then we measure J. We look in which interval J is. So we will find what is the interval, and we will encode the value of the interval, the label of the interval, into a classical memory. When we find the value J, we will have a certain quantum state that depends on J. We will first convert this into the value of the angular momentum corresponding to the interval, encode that into the memory, and then finally decode. So overall, this protocol uses log n qubits and 1/2 log n bits for a total of 3/2 log n if you just look at the overall memory. So to conclude, I have a little bit of a puzzle for you. So I just showed to you that for qubits, when you know the spectrum, the best compression, the smallest memory size is of order log n. If you don't know the spectrum, the memory size is 3/2 log n. So how many of you can see here a general pattern? How many of you have an idea how to generalize this for higher dimension or different families of state? Does anybody? I would not have had it just by this, but so let me give you a hint. So log n is 2/2 log n. 3/2 log n is 3/2 log n. So what are 2 and 3 here? If you know the spectrum, this is the number of parameters you need to specify the state. So if you know the spectrum, you are in a shell of the Bloch sphere. If you don't know the spectrum, you have an arbitrary point inside the Bloch sphere. So it's 3 parameters. So it's natural to conjecture that the optimal thing will depend on the number of free parameters in general. So this brings me to the last slide. So a natural conjecture is that at the leading order, whenever you have a certain parametric family of states, the total memory size that you need will be equal to the number of free parameters in this family divided by 2 log n as the total memory size. So this was the conjecture that we had. And the good news is that we proved it. So this is a result that was on the archive last week. So we just proved that this conjecture is true. So this is the ultimate amount of bits, of qubits that we need to compress a generic family of states for n copies. So this result has also a little bit more than just the rate. So we can also split the memory into quantum and classical bits, depending on the structure of this family of states. And we can also show that we can reduce the ratio between quantum bits and classical bits to be as small as every finite positive constant. So we can reduce the amount of qubits to be negligible compared to the number of bits, but still non-zero and actually growing always like a log n. So this is, we have an intuition that this is actually the best that can be done. So that's all I wanted to say. So I leave further comments on this for our discussion now. So thank you for your attention.
questions for Giulio? Oh.
Thank you. I guess I have two questions. Is this result just for qubits, or is it general for any qubit?
The last one?
Yeah.
Thanks a lot. No, it's general.
Oh, great.
For every finite dimensional system.
I see.
We have it, yes, the only limitation so far is that we can handle only finite dimensional systems. We have specific results for infinite dimensional systems like displaced thermal states, coherent states, but we don't have a completely general result in infinite dimensions. So I suspect the result should still be true. I think this is a pretty fundamental fact that I expect to be true. But for the moment, we can prove it only for finite dimensional quantum systems.
I see. That's awesome result. So another question. In the case of qubits, I mean, in the first scenario, you assumed that you know the spectrum.
Yes.
Right. So one naive approach to do compression is just to use this protocol for purifying qubits by Eckert, Sirac, and collaborators. So first purify the qubit and then compress. We know how to compress pure qubits. I was wondering if you use that approach, do you get the, do you know, I mean, the rate is comparable with what you
This is a good question, but I must say I haven't tried, so I cannot really guess now. I mean, this...
Because their protocol is reversible and optimal. It looks that you don't lose anything using their purifying protocol.
Yeah, actually, it may be that this is actually what it is, because what we showed, just to remind the result, is that n copies of the same qubit states are actually equivalent to a Gibbs state of a particular spin J system. So like you can always think of rho tensor n as this particular rho J for a fixed J. Right. So at least from this point of view to the purification, I think just doing this should not hurt the purification protocol. So probably the two things turn out to be equivalent.
Because the protocol, the purification
because we can always think of the n copies as just their compressed version that we have here.
Exactly. Because that protocol is also reversible and optimal. I mean, you don't lose anything by using that protocol.
Well, there is always, because when you talk about optimal purification, you really care about the fidelity.
Right.
So now the error here is 1 over square root of n. The fidelity of purification typically varies on scales of 1 over n. So it's not automatic that we can make statements from one thing to the other.
I see.
Because the errors are of different orders. But at least morally and intuitively, I think it should actually work.
Okay, yeah. Thanks.
I have two questions. So the first one is, do you like, or this is more like curiosity about the proof. So you say f is the number of free real parameters. Mm-hmm. So what is your exact regularity assumptions on the ensemble? Because if you put like a fractal or something, then probably you end up
Now this family of states needs to be smooth enough. So I think to be safe in my answer, I think like having second derivatives in all the parameters, this should be enough for the result to be more precise. Your question just stimulates me a more conceptual comment. So this is really the meaning of this result is really that the amount of information we need to store the state is literally equal to the amount of information that we need to describe the state, even if we know what the state is classically. Because, I mean, this is pretty much like the number of parameters you need to write down the state up to a certain precision. So this really tells you that describing the state and compressing the states are one of the same task, at least for this problem. Yeah.
And my second question is, maybe you can shortly, of course I can also just read the paper, but maybe you can shortly indicate how you do this reduction of the quantum part to an arbitrarily small positive.
Yes, so that's a very good question. I intentionally omitted a little bit of the details about this because this paper really uses techniques that are totally different from those that I presented in the rest of the talk. So the techniques we use here are not based on symmetry, not based on Schur-Weil, not on anything that I showed here, are essentially based on three main ingredients. One is sample optimal tomography. So we first get a rough estimate of what the state is, which will turn out into classical bits in the end. So that's and the next thing that we do is to use a result that is called the quantum local asymptotic normality, that tells that if you know pretty much what is your state, if you know rho x up to some small error, and you have many copies of this, rho x tensor n can be asymptotically converted into a Gaussian state in infinite dimension, where there is a classical part and a quantum part. So this is pretty much where the separation between classical bits and quantum qubits comes, because then we separate, we compress separately the classical part that comes from local asymptotic normality and the quantum part. Then the third ingredient is to use optimal quantum amplifiers to make up for the loss of qubits that we had when we did the tomography. So we just ramp the number of qubits up again using amplification. Thank you.
Okay, we should probably stop now. Let's thank Giulio again.
Thank you. Thanks.